Okay, so far in chapter 4, we've talked about congruent figures, mostly triangles. We started proving triangles congruent by side, 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 angle, and angle, side. Nothing special about the triangles other than the fact that they're congruent, if we could prove it. But in section 4.5, we'll be working with isosceles and equilateral triangles. So we'll first start with isosceles triangles. We know that on an isosceles triangle, two of the sides are congruent, right? That's what we think of when we think of an isosceles triangle. Well, it just so happens that when the two sides are congruent, the angles across from the two sides, which we're calling the base angles here, are also congruent. The angle formed between the two sides that are congruent, that's called your vertex angle. So you've got a vertex angle, you have your base angles. The two sides that are congruent are the legs, and the other side, the third side, is the base. It's not always sitting on its base. It could be upside down, and even if it is, it's still considered the base. So the isosceles triangle theorem is stating that if you know these two sides are congruent, you don't have to be told that the two base angles are congruent. They just are. If it's an isosceles triangle, or if you only know that the two legs are congruent to each other, you don't have to be told that the base angles are congruent. They just are. And the converse is also true. If you know two angles in a triangle are congruent, those would be your base angles, and the sides across from the two angles would be congruent. So that's the converse. Angle A is congruent to angle B. If angle A is congruent to angle B, then side AC is congruent to side BC. So it goes either way. So we're trying to figure out if GK is congruent to we're trying to see if GK and HK are congruent. And so to determine that, we just need to focus on the smaller triangle. And in the smaller triangle, we see that this GH is the base. These are your base angles. They're congruent to each other. So if angle G is congruent to angle GHK, then the sides across from the two angles, which would be GK and HK, would be congruent. So the answer is yes. GK is congruent to HK because the base angles are congruent. What about HL and KJ? Let's see. HL and KJ. Can we tell if those two are congruent? No, not enough information. Well, quadrilateral. Okay. Next. So to find the value of x, we have two expressions here, and we have to set up some sort of equation with the two expressions in it. So we have to find things that are equal to each other. When this triangle, the base angles are congruent to each other, which means the sides across from those base angles, which would be the legs, would be congruent. So we could say that 7x minus 10 is equal to 3x plus 6. Solve that for x. Subtract 3x from both sides. 4x minus 10 is equal to 6. add 10. 4x is equal to 16. Divide by 4. X equals 4. After working all those proofs, I almost forgot how to work with numbers.
Could you add 10 and subtract 3 like in one step? Or like to
Just see here. Usually people who do that will make a mistake with their signs or something, so be careful doing that. Okay, so let me show you some more examples that you might see that I don't have a regular example for with the isosceles triangles. So if you have a triangle, an isosceles triangle, and you know the vertex angle, you might have to find the base angles. Well, if this is not here, with it like this, you may know right away what to do. But let's just say that it looks like this, and I go, okay, what's the measure of the base angles? Well, it may be helpful to see that x is in the place of the base angles so that you can set up an equation. So it'd be x plus 40, right, equals 180. So that's 2x plus 40 equals 180. Subtract 40. We'll go back to not having to show all of that. And get 140. Divide by 2, and x equals 70. So quickly, if it's this simple, you can subtract 40 from 180, and you get 140, and divide that by 2. Because you're splitting up. When you subtract 40 and get 140, that means two angles that measure the same have to equal 140, so you would divide it by 2 and get 70. And then it's easier to find the vertex angle if you have the base angles. And you may only be given one of the base angles. But you know they're both the same, so if one's 50, the other's 50, and so then you would add those up and set them equal to 80. Alright, next. Okay, we're trying to find the measure of this angle, angle S, and we only have the measure of this angle. Can we determine by what we have up here so far, the measure of this angle, angle LNS? Do we know the measure of that angle?
Yes.
What is it?
50.
How do you know that? What is it? We don't know that LP's parallel to SN.
They're both the vertex angles of the isosceles angles.
Okay.
And the triangles are congruent.
That's what I'm looking for. The triangles are congruent to each other. You can still have two isosceles triangles that have the same length measures and have different angles here and here. But because the two triangles are congruent to each other, this is very important. We could not work this problem if we didn't know these two triangles are congruent to each other. So usually when they give you information like that, there's a reason for it. So if we know that these two triangles are congruent, then the two vertex angles are corresponding angles, which makes them congruent. And yes, they end up being alternate interior angles, but we don't know that. We can't determine that just by, we don't know that this is parallel to this, but if you look and see that the two triangles are congruent, you could determine it that way. So to get the base angles, now we can just focus on this triangle. It may be helpful to put an X here, and if you put an X there, go ahead and put an X in the other angle because those two angles are congruent since they're the base angles of the isosceles triangle. So you have X plus 50 equals 180. 2X plus 50 equals 180. 2X equals 130. So what's half of 130? 65. And you can double check that. It's 65 plus 65 plus 50, 180. Okay? Probably should put angle S is equal to that since we used X to show that angle S is equal to X. Okay, next we have another thing about isosceles triangles. So if you take just any triangle, and you bisect just on an irregular triangle, an oblique triangle, and you bisect an angle, a vertex. You cut that angle in half. Notice how there's nothing significant about where it hits on the other side, and that may not be perfect, but you can kind of tell. Maybe that should be more like that. If this is congruent to this, that doesn't mean that this is congruent to this, and that doesn't mean that this hits it perpendicularly. We don't know. Actually, we know it doesn't because it's not an isosceles triangle or an equilateral triangle. But if you have an isosceles triangle, and you bisect the vertex angle, it does more than just bisect that angle. It hits the other side at a 90-degree angle, and it bisects that side. So an angle bisector of an isosceles triangle, if it's bisecting the vertex angle, cuts the angle in half, hits the other side at a 90-degree angle, and cuts that side in half. So that angle bisector is also a perpendicular bisector. So you would need to know this. If you have an expression here and here, you would set them equal to each other to solve for x, or maybe you have an expression for this angle. What if this said 2x plus 20? What's the value of x? Set it equal to 90 because it's a 90-degree angle. Stuff like that is what you would do with a problem like this that involves that theorem. Last thing, equilateral triangle. Equilateral triangles are very special. an equilateral triangle means, what does lateral mean? What do you think it has anything to do with the angles or the sides of the triangles? Equilateral, the sides. Equilateral, you're saying that all three sides are congruent. Well, also is equiangular. An equilateral triangle is also equiangular, but we don't call them equiangular triangles. Because if it's one, it's the other. If it's equiangular, it's equilateral. If it's equilateral, it's equiangular. So in an equilateral triangle, all three sides are congruent. All three angles are congruent. Can the side measures change? Can you have different size equilateral triangles? Yes. So we don't know, but if we do know the measure of one, we know the measure of all three. What about the angles of an equilateral triangle? Can they change? They're always going to be 60. So you take 180 divided by 3 and you get 60. So no matter what, no matter how small the triangle is, no matter how large the triangle is, in an equilateral triangle or equiangular triangle, all three angles will be 60 degrees, always. You don't need, so you're normally, on a problem that has an equilateral triangle, you're not going to be told the angle measures of an equilateral triangle because you're supposed to know that. All right, so we didn't really do an example with this, but that's what you have to know to work any kind of problem. So you'll use missing measures to find other measures. So you have an equilateral, an isosceles triangle. An isosceles triangle has two legs that are the same length. The other side is your base. And where the legs meet the base, that would be your base angles. And the other angle on top between the two legs would be your vertex angle. So you have vertex angle, legs, base, base angles. Base angles are congruent if the legs are congruent. Legs are congruent if the base angles are congruent. And there's your assignment.